Let's say we're rolling a 6-sided die. Is that fair? Well, we say it's fair if each outcome is equally likely. What if I roll 2 dice and add them? Is it also fair in that every possible sum is equally likely? Thinking about it, you can get to certain numbers in multiple ways, so probably not. But what if I get more dice? Continue to roll all of them and add them all up. Will I ever reach a point where each outcome is equally likely? Kind of like how it was for one die? So instead of talking about what this could be with words, let's get some data about this. Here, the x-axis represents all the possible sums when rolling some dice. The y-axis is the count divided by the number of rolls for a given outcome. And the curve is the theoretical density we would expect to see. And for one die, we see exactly what we expect. Each outcome is equally likely. But as the number of dice rolled increases, we can notice how the points mostly follow the curve regardless of how many dice are rolled. Wait, but how did I get this curve? Well, there so happens to be a theorem about that. Whatever this theorem says, let's frame it in the context of some dice. Each dice is a unique random variable, and so when we add them all up, we will expect whatever shape this makes to be increasingly normally distributed the more dice we roll. But this is only on the condition if every random variable is independent and identically distributed. Side note, even though the statement of the theorem uses the sample average, the main idea is that you're adding a bunch of random variables together, and from this you can apply it to averages. So why does it approach a normal distribution rather than some obscure spread? Well, before that, we need some ideas about moments and moment-generating functions. Moments. You probably heard of at least one of them. The average, maybe the variance. Well, they're all measures of a single random variable. A moment is defined as something that looks like this or this, and it depends on whether or not it's discrete or continuous. The moment-generating function is a way of encapsulating all possible moments into one function. I'll call it the MGF for short. And by using the Taylor series for the exponential function, we can tidy up the definition to look something like this. Taking the kth derivative and set t equals 0, we can see that we get the kth moment. There are still two key properties we need to know about the MGF. One is that the product of two MGFs looks like this, and that the convergence from one MGF to the other implies that the distribution converges from one to the other. And with these tools, you can have some big idea of how it can be shown that a random variable will have a MGF that converges to whatever the MGF is for the normal distribution. A normal distribution has two parameters, mean mu and variance sigma square. But if we start by standardizing, we can begin with the assumption that the parameters are mean 0 and variance 1. And typically we label standard normal with z, and this gives us the MGF that looks like this. Rushing through the algebra, this is the derivation. First, we need to find the mean and variance so we can standardize S, which we'll call S star, and this is the random variable we want to find MGF of. First, we'll do some algebra before expanding the definition. Next, we'll bring out a Taylor series representation centered around 0. Then we truncate up to the second power and simplify. Finally, we notice that this looks like the MGF for standard normal. So this implies that as n gets bigger, the MGF converges to the MGF of standard normal, which then implies that S star converges to standard normal. So why does this matter? Well, notice we haven't said anything specific about the xi. We only really require for them to be independent to each other and to have all the same distribution. This isn't guaranteed to happen, but it's not too difficult to find either. The second assumption requires that the unknown distribution has an MGF that exists, which is also an easy requirement. Because of these two relatively flexible assumptions, it's pretty easy to find a situation where the central limit theorem applies. So even if we don't know the distribution of some big dataset, we can rely on tests that assumes normality if they also satisfy the conditions for the central limit theorem.